Okay, that should be working now. So hi, I'm Zoe, and this is my talk on the GRIN backend for Idris2. I started writing the backend a while ago, like possibly even a year ago, not sure exactly, but I started it because I was interested in like compilers, and yeah, so GRIN is a intermediate representation. That means so in a compiler you've got multiple like stages or like intermediate representations. They're just different ways of representing the code, and they get like more low level as you go along. GRIN is a very simple IR with and as it says, it's got a monadic like sort of structure to it, which yeah, and that makes it easy to optimize. So here's an example of a GRIN program, and I'll go through it line by line. So the first like 2 lines, these two, that's declaring a external function, and it has a type int to unit. And then this next function adds 4 to an integer. So you've got the function and you've got the arguments, and then you can basically imagine it's a do block, even though it doesn't say do. And then the factorial function, example, this is how it's represented in GRIN. It's quite like it's very verbose code, because everything has to be on its own, like with its own binding. Okay, so one interesting change that GRIN makes to the previous, like to higher level representations of code, is defunctionalization, which is basically removing closures from the code. So whereas in Idris you might have a lambda in a normal form, which is the IR that I compile to GRIN, it's represented as a partially applied function. So that might be, for example, a function pointer plus the arguments or some. But in GRIN, it is just a normal constructor. It doesn't store the function pointer anywhere. This like transformation requires the whole program to be available when you're compiling. However, this requirement, it might be able, there are possibly ways to relax that requirement. But GRIN doesn't do that yet. So the whole point of GRIN is to optimize functional code more than it can currently be. And the way GRIN is structured is there are many small optimizations and simplifications, and some like quite complicated analyses. For example, heap points to analysis, and the one use of that analysis result is generalized unboxing. So heap points to analysis. This works well in GRIN because in GRIN all of the control flow is very explicit. There's no like when you're calling a function, you always know exactly what functions you can be calling. Compared to, say, Haskell's IRs, where it could call any function, you can't necessarily know what functions there are. So whenever you apply a closure, heap points to analysis can work out what subset of all of the possible closures can be called that apply function. And that means the generated codes can be a lot faster. It also allows closures to unbox the argument, the values that they return, and also unbox the arguments. And that can massively speed up code. So let's take this example function, which, all it does is add 10 and 20 and print the result. But this is the sort of code that, say, the Idris2 GRIN backend might produce. So it's got lots of, it's got to make a pointer to the integers and store them on the stack, and then it partially applies the foo function and applies it to the different closures. And one thing, the apply function is a special function which applies a closure to an extra argument. The GRIN optimizer tends to apply this before running heap points to analysis, because heap points to analysis is it's context insensitive, so it doesn't depend on where it's called. So you have to inline some functions to get the best results. So here is an extract of the results of heap points to analysis for this for the code I showed, and it's worked out that the first time apply is called, it's only ever called with the foo function applied to no arguments. And the second time it's called, it's applied with foo only applied to one argument. And that 0 there is it's what store instruction the argument is from. And because we now know exactly what constructors appear at each call function, we don't need a case statement. We can have completely linear control flow. So as you can see, it generates this code after some other optimizations. And that is a lot more efficient. What's next? Yes, another use of heap points to analysis is generalized unboxing. So generalized unboxing in GRIN is two optimizations. One is unboxing the return values. So rather than returning the C int constructor applied to the actual value, which would take up two registers, it instead just returns the value. So that's a lot. Well, that reduces that makes it faster. And and the call site, this sort of shows how small optimizations are. The optimizations are all written to be easy to write, and then there's other optimizations that cleans up the potentially slow generated code after each optimization, and they all work together to make code a lot faster. And the other part of generalized unboxing is called arity raising, which splits up arguments. So, and it splits up arguments, and it loads arguments, which means arguments that were previously passed on the heap now get passed on the stack or in registers. So rather than calling fetch, which loads something from the heap into the stack, in the plus function, it instead does it in the main function. But because there's a store and then immediately there's a fetch, GRIN would later be able to optimize that to completely get rid of all of the heap allocations. So that's all my slides. I'll now demonstrate the GRIN backend compiling some Idris code. I think I'll have to change this. Yeah. Okay, so yeah. So here's a test program, which a test Idris program which calculates the sum of the integers from 0 to 10. If we compile, currently the Idris2 GRIN backend can't compile programs, but it can interpret and optimize programs. So yes, it came up with the correct answer, which is good. And we can have a look at the... So here's the GRIN that the backend produces directly. It's not very optimized. There's a lot of it. And then the GRIN optimizer has reduced that to more than I would expect, but still less. Yeah. Let's see. So here, this optimization, trivial case elimination, this uses the result of heap points to analysis. So for example, oh, that's not the optimization I was thinking of. That's the one actually. Sparse case elimination. So as you can see, it's removed a lot of constructors from each case statement that is worked out can't be there. So this has removed a lot of closures that can't appear there and other things. So now it's only left with integers, and that means it will be able to get rid of the entire case statement later. And again, this has worked out that the only the only constructors that can appear here are the constructor for cons and nil, which are the constructors for lists, whereas previously it could have been many other things. So yep, that's all I've prepared. Has anyone got any questions?
Looks like we have one question coming in chat. Yep. I missed the beginning because something came up. Is GRIN a stack-based language? How does storing things work?
So GRIN is a definitely a register-based language. Well,
okay.
It's yeah. So store is for heap allocations.
Okay.
And fetch is for, well, the opposite, really.
Yeah. I see. I see. That makes sense. But when you say store v617, how does he know which is? Oh, never mind. I understand. Makes sense. Yes.
So QQLQ has asked if GRIN can evaluate the entire program to 55, is it possible to use this for constant folding? Yes, constant folding is definitely possible. I don't know if the current GRIN optimizer has implemented that yet, because it's a well researched optimization. Whereas a lot of the other optimizations are not so well researched and not implemented yet. So the people who wrote the GRIN optimizer wanted to check that those actually work for real world programs first. Matt Paulson has asked if show scheme does a lot of optimization, and he asked if GRIN can do some novel things that Shay doesn't try. Yes, GRIN can do various optimizations that Shay doesn't. I think. I don't know the exact list of optimizations Shay scheme does, but I think GRIN can optimize closures better because of defunctionalization. Shay represents a closure as a function pointer and a list of arguments that it's already been applied to, whereas GRIN represents it as a constructor, so then like trivial case elimination and stuff can make that a lot faster and potentially remove the closure entirely. Has anyone else got questions? Andre's asking what other languages use GRIN. So currently Shaba Huska is writing working on the compiling Haskell code to GRIN. So that could mean good Idris to Haskell interop. I don't know of any other languages that are wanting to compile to GRIN, though. Because GRIN is a fairly new technology. What kind of executables can be produced with GRIN? Well, currently GRIN compiles to LLVM, and LLVM can compile to all manner of things like WebAssembly or native code. Currently, GRIN doesn't feature a runtime really, or at least a very minimal one, so there's a bit of support code that's needed to get the compiled GRIN code to run. Does GRIN include debug info? I don't know if it does. I don't think it currently has a way to relate the GRIN code to the original Idris code, though, if that's what you're asking. So micro benchmarks for Idris. I haven't made any benchmarks for the Idris2 GRIN backend. But there are benchmarks of the original. There have been, I think, at least two papers on GRIN, and I think they both have some benchmarks comparing GRIN they've generated from one of the Haskell compilers to GHC and some other Haskell implementations. So GRIN is being used for Haskell. It does have special support. Well, yeah, it does have special support for laziness. I will just quickly write something to show that. Oh, what happened? Oh, yeah. Okay, so if we have a look at the code, if you look at the code for, hang on, oh, it's going to be here, isn't it? That is not what I was expecting. But yes, GRIN does support lazy code. Unfortunately, I haven't been able to demonstrate it brilliantly here. So there's a function in GRIN called update, which it overwrites some pointer with a new contents, and that is how. So laziness. So a thunk, as you can call it. So a lazy expression of a thunk is represented as in a similar way to closures are. So it's a constructor. For example, might be like, say, so that generally the convention is if it's a lazy thunk, it starts with F. It might be F. So that could represent a lazily adding 10 and 20. And then you would update lazy int the heap. Well, that's a pointer to that. And you'd update it to be, and then to be like that. So update is built into GRIN. I hope that answers the question. So what do I think of Kindelia / HVM? So HVM is it's a higher order virtual machine, if I remember correctly. And so I think it has possibly got some potential. But it is still kind of an interpreter, really. But it can still be quite efficient. I think we'll need to see it mature a bit more, because that same idea has come up before, and I don't think it led anywhere previously. But if they can get a runtime that can compile programs, then definitely it could work. They often try and people try to sell it with the optimal reduction, which in some cases means it can be a lot faster. I don't know how many cases it would actually improve that much, though. But yeah.
Okay. Are there any other questions? Is there I think this obligatory mention your stuff at the end. Is there like two things? Is there a repository where we can look at this? And the second thing is, if someone wants to help working on this, what can they do to help and participate?
Yes, it's on my GitHub. I will post that after the talk. In terms of helping, well, if someone wants to go through all of the code and clean it up a bit, that would be great, because it's not very readable at the moment, because I basically rewrote it 3 times but kept some of the old code, so it's all a bit of a mess. In terms of what's needed, I will have to think about that some more. But if someone does want to help, let me know.
Sure. So can people just DM you on Discord?
Yeah.
Do you have like a website or Twitter or something that you want to share?
I don't have a website other than my GitHub repo. GitHub.
Cool. Great. Thanks a lot, Zoe. It was great. I'm very happy to see more backends. I'm very happy to see more people giving presentations. And with that said, we'll let you go, everyone. I suspect if you have any questions, send them to Zoe. She will be happy to answer, I'm sure. And we'll see each other next month with the next presentation.